Okay. Okay, can you hear me well? Okay, good. Sorry for the technical problems. So my name is Jana. I'm a PhD student from Prague, Charles University, and I'm happy to share with you our ongoing project about evaluating wall shear stress together with my supervisor Jaroslav Hron and Jorgen from here. Okay, no, this one. So let's start with the motivation. So why do we care about evaluating wall shear stress? So our motivation arises from application in brain aneurysms. Aneurysms are abnormal bulge in arterial walls that affect approximately 3% of the population. And the bad thing about aneurysms is that they can burst, which is then very, very bad for the patient. So medical doctors need to know whether to preventively treat the patient or not. And they have a whole lot of risk factors. One of the class is called hemodynamic risk factors. And the most commonly studied hemodynamic quantity is wall shear stress. So that's why we care about it. Let me now briefly show the computational workflow. So the patient first needs to undergo a CT scan. Then we can, from these images, generate a computational mesh. We're using tetrahedral meshes generated via Gmesh and VMTK software. Then we can run the simulation, the incompressible Navier-Stokes equations. We are using Legacy Phoenix together with the solver from PETC library. And we use a P1 stabilized element with interior penalty stabilization. And for this presentation, the key point is the post-processing. So from the velocity and pressure, we can evaluate the wall shear stress. And in particular, I will present two different methods for computing wall shear stress, which is boundary flux evaluation, a rather new method, I would say, and a standard method, which I will call projection method. So now I will describe what the boundary flux evaluation looks like for a simple 2D Poisson problem, just to have the key idea in mind. And then we will go to Stokes problem and then Navier-Stokes. So let's consider this simple Poisson problem on a unit square mesh with Dirichlet zero boundary conditions. So the first step of boundary flux evaluation is to write down the weak formulation and discretize and solve for it, right? So far, so good. And then the next step is to relax the zero boundary condition on the walls and assume a Neumann boundary condition, and then ask which flux needed to be on the boundary so that we satisfy the zero boundary condition for this. Oh, I'm sorry. I can't move. I'll just stay here. Okay, so once again, because this is really the key idea of this presentation. So first, we assume a zero boundary condition. We solve for the weak formulation of the problem. Then we no longer assume the zero boundary condition. And on the right-hand side, we already have the solution from the previous step, and we seek for the flux over the boundary, the function g. So we want to approximate the Neumann boundary condition. You can think of it like that. And the guy who did it before is Graham Curry. So this paper is really amazing, and we took this example from his paper. So once again, the boundary flux evaluation looks like this. And to ensure that we can solve for it, we assume that GH, the flux, lives in the same space as our velocity. So for the for P1 velocity, we assume P1 flux. And the second method, the more standard one, at least for Wall shear stress, which I'll talk about later, is simply to project the Neumann boundary condition, which is gradient of u dot n. So these are the two methods that we will compare on the unit circle on the Poisson problem. And here we see the domain, and we will evaluate the error only over the bottom boundary. And here we can see the convergence rates for the projection method, which is more or less 1, equal to 1, and for the boundary flux evaluation, which then converges with rate 1.5. And we can realize that in this problem, the troublemakers are the corners. So, and this is already what Kari did in his paper, so we just replicated it. So we can compute the error only on mid half of the boundary, because in our real applications, we are also not that interested in inflows and outflows, only in the part of where the aneurysm is. So we are okay with that. And we can see that the convergence rate for the projection method didn't really change, but we achieved an order of 2 for boundary flux evaluation, which is great. So let's now move to Poisson flow in a cylinder. So it's a more complicated problem in a more complicated 3D geometry, but still simple enough. So here we can see the stationary incompressible Stokes problem. And let's do the same procedure as before, but with this problem, with 0 velocity on the walls as before. So this is the weak formulation. And so step 1 is to solve for velocity and pressure. And step 2 is to use velocity and pressure from step 1 and seek G, the Neumann boundary condition, the flux over the boundary. And now we can realize what is G in this problem. T, of course, is the Cauchy stress tensor. And Tn is the traction force that acts on the boundary. So in fact, the boundary flux that we seek for is the traction force for this problem. And then we realized that, okay, Wall shear stress is the tangential part of the traction force. So to evaluate Wall shear stress, we somehow need to obtain just the tangential part. So our idea was to simply subtract this normal part of the traction force from the right-hand side. And for this, we use the formula for Cauchy stress, right? So this is the key idea of computing Wall shear stress using the boundary flux method. And I'll just remind you that the projection method will be done simply by L2 projection of the term Tn, the traction force. And similarly, the Wall shear stress will be just a projection of the tangential part of the traction force. Okay, so let's see the results. The results are not nearly as it was for the 2D case, which is yeah, it is what it is. So we used P1 element with interior penalty stabilization, and we saw that both methods converge with roughly the same convergence rate of 1.3. So it was a bit worse for the boundary flux, but a bit better for the standard evaluation. It might be caused just by the nature of the problem, the Poisson flow, because pressure gradient is linear, so is the traction force then. And now let's have a look at wall shear stress results for the same problem. So I think I didn't mention it before, but if we compute the boundary flux evaluation, where we assume that the boundary flux lives in the same space as velocity, we can then project it to a different kind of space. So here on the right, we projected it to DG0 function space. And then we see that the boundary flux evaluation is much better than the projection method for the same function space, DG0. And on the left, we see the a similar results as before for the traction for wall shear stresses. Okay, so now let's move on to the full Navier-Stokes problem in real geometry. So the full system looks like this. We have the convective term and time derivative here. The Cauchy stress is defined like this. And as before, we have zero velocity on the walls. Now I won't write the equations again. The procedure is exactly the same. And let's just show results for boundary flux evaluation and projection on the same mesh. So here we can see that the boundary flux evaluation overestimates the wall shear stress in this region where the velocity jet hits the aneurysm. But this only happens for coarse meshes. If we refine it, make the edge length smaller, and even the finest mesh, which looks like this, we can see that both methods show the same result, so they are consistent. Okay, so now to sum up, I think I convinced you that boundary flux evaluation can be used for computing wall shear stresses. And we did compare boundary flux and projection method on two problems with known analytical solutions. And even for the 3D geometry, patient-specific geometry, the methods show good agreement. And maybe it's good to mention that the computational cost for both methods is the same. So now some outlooks. We would like to do the same for different finite element discretizations, for example, Taylor-Hood. We already tried to do it, and there's something fundamentally wrong with it. So if you have any ideas why the weak boundary flux doesn't work for Taylor-Hood, please come to me and let's discuss it. So thank you for your attention.